Good morning, everyone. Let me introduce myself first. I'm Khoirunnisa. In this occasion, I'm representing my team to present our research about mathematical model of COVID-19 transmission through virus attached to non-living media by considering virus growth inhibition. COVID-19 is an infectious disease caused by SARS-CoV-2 or coronavirus. In March 2020, World Health Organization announced that COVID-19 is a global pandemic. There have been more than 546 million positive cases and more than 6 million deaths worldwide by 4th July 2022. Transmission of COVID-19 occurs through interaction between animals to humans or between humans. Droplets, close interaction, and things exposed to the virus can become a media of COVID-19 transmission because the virus is stable for several hours to days in aerosols and non-surfaces. The virus may infect people after touching contaminated non-living media. Many researchers have established numerous models for COVID-19 under the different concepts of fractional calculus, such as the SIR model to characterize COVID-19 transmission. But the models still focus on interaction between humans as the main cause of COVID-19 transmission, and have not considered COVID-19 transmission through non-living media along with the effort to inhibit it. In this research, we construct a three-dimensional ordinary differential equation system as a new mathematical model representing the interaction between virus, susceptible, and infected subpopulations to investigate the impact of inhibiting the growth of the virus attached to non-living media on COVID-19 transmission. For model variables, we have four variables, V, S, I, and Z. The interpretation of the model variables are shown in the table. For model parameters, we have 8 parameters as shown in the table. Now, for the mathematical model. On this side, we have the compartment diagram of the interaction between virus, susceptible, and infected subpopulation. In this side, we have three equations. The first equation, dV/dt, represents the rate of change in the virus population with respect to time. The second equation, ds/dt, represents the rate of change in the susceptible population with respect to time. And the third equation, dI/dt, represents the rate of change in the infected population with respect to time. We found two equilibrium points, the disease-free equilibria, which represents the absence of endemic in a very long time, which exists for all conditions. And second, the endemic equilibria, which represents the existence of endemic in a very long time, which exists for A is greater than P. The local stability analysis for EO are identified as follows. If A is greater than P, then EO is saddle. If A is less than P, then EO is stable node. For the EI local stability, suppose A is greater than P. If this condition is fulfilled, then EI is stable node. For the second one, if this condition is fulfilled, then EI is stable focus node. For the coexistence of equilibrium points, suppose A is greater than P. If this condition is fulfilled, then EO exists in saddle condition and EI exists in stable node condition. If this condition is fulfilled, then EO exists in saddle condition and EI exists in stable focus node condition. For the numerical simulation, we define the difference between the growth rate of the virus and the inhibition rate as delta. A minus P equals delta. We study the effect of virus growth inhibition rate in overcoming endemic in population by investigating the existence and local stability of EO and EI, and also dynamics around them as delta varies. Phenomena that occur in the population are divided into three cases based on the variation of delta. Region A, when delta is less than 0, region B, when delta equals to 0, and region C, when delta is more than 0. In region A, shows that EO is the only equilibria that exists under the condition, while EI does not exist because it contains a negative value. Based on the local stability condition of EO, if A is less than P, each subpopulation that has a value around EO will be equal to EO, which is the disease-free equilibria that has a zero number of infected subpopulation. It means that if virus growth rate is less than its inhibition rate, then endemic will disappear. Dynamics in region B shows that EO exists and EI still does not exist, but almost exists because a transcritical bifurcation point is found in this region. In region B, transcritical bifurcation occurs as delta increases until delta equals to 0, which is equivalent to A equals P. The condition when virus growth rate is equal to its inhibition rate becomes threshold of non-endemic condition, namely the minimum condition that may occur so that endemic does not appear. Dynamics in region C represents coexistence between EO and EI, shown as some phase portraits of the solution around them. Dynamics of the solution around EO are connected with dynamics around EI. Based on the local stability of EO, if A is more than P, some solutions whose initial values are around EO will converge to EO, and the other solutions will diverge from EO and converge to EI. It shows that if the number of each subpopulation is around EO, there is a possibility that endemic will disappear or remain exist. Besides that, every solution whose initial value is around EI will converge to EI. The number of each subpopulation that has a value around EI will be equal to EI, which is the endemic equilibria containing non-zero number of infected subpopulation. It means that if the number of each subpopulation is around EI, then endemic will remain exist. For the conclusion, people can be infected by COVID-19 through their interaction with the virus attached to non-living media. If virus growth rate is less than its inhibition rate, then disease-free equilibria exists in stable knot condition, and endemic equilibria does not exist. It represents disappearance of endemic in population when the number of each subpopulation is around disease-free equilibria. If the virus growth rate is greater than its inhibition rate, then disease-free equilibria exists in saddle condition, and endemic equilibria exists in stable or stable focus node condition. It describes two phenomena. Possibility that endemic will disappear or remain exist when the number of each subpopulation is around disease-free equilibria, and endemic will remain exist when the number of each subpopulation is around endemic equilibria. Virus growth inhibition rate must be greater than virus growth rate, so that endemic does not occur in population. These are the references. That's all for my presentation. Thank you for your attention.